Good morning. Here we are. It's the physics video lecture. Physics 105B video lecture 23. And we're talking about rigid body motion, the inertial tensor, all kinds of interesting stuff. So let's review briefly. So the motion of the rigid body we began this time by having a lab frame and some rigid body here that has its own system of body axes. And we had a vector going to the center of mass there, call it r this time if we want. And then we have three more quantities. You could define them using the orientation of the one coordinate system to the other. So we have 6 quantities, and we remind ourselves that when we were doing systems of particles, we also had 6 quantities. Okay. So one of them was mass times acceleration of the center of mass is equal to the net force. And the other one was the rate of change of the angular momentum is equal to the net torque. So that's true for systems. But we then have to do a number of things to arrive back at these. Actually, this one we can ignore for the most part, right? We know this, what a center of mass does, what a particle does, what an object does. But in terms of here, we have some steps to take till we actually get to the rotation of this thing, because the angular momentum, which we have defined as the sum of all the angular momenta, has to be brought into connection with the angular momentum of a rigid body. Right here, this is just the sum of the myriad individual angular momenta that comprise the rigid body, of the particles that comprise the rigid body. And we don't yet have the axis of rotation. So that's actually the next thing. So this was the first step. The second step was then an infinitesimal displacement. Where we introduce the actual axis of rotation and then the angular rotation. So we had this, I'll just repeat what I had. It was a board that is brought into a displaced and rotated position. So that equaled just the displacement, but it then also was equal to what I called this rotation here, right? This d theta rotation. Now, since we're in the board, it's very clear that the axis of rotation associated with this is just out of the board. But for an object, a three-dimensional object in three-dimensional space, the displacement, which is more or less trivial for us, is one thing, but the rotation is about an instantaneous axis of rotation that isn't necessarily coming out of the board, right? Think of a different type of twist to this thing. So this d theta is defined in terms of the infinitesimal displacement, but we don't really yet know how to calculate it. So we've got the d theta, and then when we did divide by dt, we ended up with this omega was that d theta divided by dt. We're going to have to get some dynamics for this thing, okay? But otherwise the construction is fine. So then, in terms of that omega, we got a really important formula for any vector A. We can talk about its derivative in the lab frame or its derivative in the body frame. And the formula that we got for that was time derivative in the lab frame is equal to the time derivative in the body frame, which I'm just referring to with this prime, plus omega cross A. Okay. So we're going to use that later. But one consequence that came out of it was that the rate of change of omega itself was the same in the lab frame and in the body frame. And by and by I have a really nice illustration of that. Okay, then, and this is getting to where we were at the end of the lecture, we were looking at the kinetic energy of the rigid body. And we came up with P is the translational or center of mass kinetic energy plus the rotational center of mass kinetic energy. And this really corresponded to the translational plus the internal kinetic energy that we had at the beginning of either the beginning of this semester or the end of last semester. Except now we're giving this concrete form in terms of our angular velocity. Write that down right there, the angular velocity. Okay. And so here we are with the expression for the kinetic energy of rotation. We ended up with 1/2 double sum, all right, ij, I sub ij, omega I, omega j. And this 3x3 matrix is called the inertial tensor. And at first, for the moment now, it looks pretty involved. So we'll have r squared delta ij minus xi xj, and this is over the body, so we can also say it's integral dm integrated over the body r squared delta ij xi xj. And I'll say in advance, it's going to be, for our purposes, we're going to treat it as a diagonal matrix, so it's not going to be that bad. I have one more important derivation of a technical nature before we dig into this a little deeper, and that is that we've found rotation. The kinetic energy expression, we also want to express the angular momentum in terms of this inertial tensor, and then we'll go to work studying it. Okay, so we have a numbering things, 5, 4. Yeah, so we have an expression for the kinetic energy. It's this very becoming familiar, right? A quadratic form, double sum for 1/2. Good. So let's go ahead and, while we're on this, do the derivation for the angular momentum as well. It's quite related to what we just did, a little bit different. But yeah, we certainly need the angular momentum. So 4, 5, angular momentum of the rigid body. Rigid body. Okay. So that's going to be a sum, kind of starting out the way we did, of m sub I r cross v, right? Or we could say r cross p if we wanted, right? So that would be the angular momentum. But now we have the rotation formalism. So m sub I r sub I cross omega cross r sub I. See, the omega carries no subscript because, as I showed before, it characterizes the rotation of the body as such. Okay. And I can probably drop these subscripts for the moment for simplicity. Having said that about omega there. Okay, this of course carries subscripts, this one does not. And now what we're going to use A cross B cross C. Let's see what we have here. Is equal to A dot C times B. Remember, this is a vector minus A dot B C. Okay. And we'll apply this vector identity to this right here. So now we have sum over M, and our A dot C is just an R squared, that's a scalar. B is the omega. And then we have minus A dot B, which is R dot omega times R. Okay. So this may be the angular momentum, but things are kind of mixed up right now because we got the omega here as a vector and here it's in the form of scalar product. What we're going to do is multiply this vector that we've defined by some arbitrary vector A. So now we're going to have L scalar multiplication with A, and then we have sum over M. We've got R squared omega dot A minus R dot omega times R dot A. And we're going to write this out in component form. In other words, as a summation. So I have sum over M, and now I'm going to have the double sum for these two vectors here. So I have sum of I and K, and this R squared will be the xi squareds with a Kronecker delta. So I have R squared omega I A K delta I K. Let's just write them out first. Minus xi omega I xk ak. So let's ponder this for a moment. Make sure this makes sense. Okay, so if you work back, you can see only when I is equal to K, you get a contribution here. And so you just have the one sum with the dot product omega I A I. Okay, K is equal to I, omega I A I. So you would collapse that one sum there. Here it's more clear, we have a dot product, so that's one of the sums, say I, and we have another dot product, so that's the other sum. That's the K there. Okay. So now, make sure we get these right. We can write I and K and see what's inside here. We have a sum over M. R squared delta ik minus xi xk, and then omega I ak. Good. So L dot A is equal to, I think I'm gonna have to exchange, let's write this down right. I have to exchange indices here. Omega K A I. So we want to make sure we can bring it into this form here. Double sum I sub I K omega K. Here I had the omega I actually, so I would have had to switch I's and K's right here. That's it. Okay. Which I can do because it's a double sum, symmetric. Okay. Yeah, and then I recognize that I've got my inertial tensor here, sum over m r squared delta I k minus xi. Okay, good. So now, so once you get here, I and k, and just change those. Now once you get here, you recognize that you've got a matrix multiplication. Right? So you've got a matrix multiplication between one, or a vector, I'm sorry, you've got that vector multiplication here. I k omega k, which I'll put like that, that is your L dotted into your A, right? Sum of A equals I 1 to 3, so this is your L sub I. No vector. So our L sub I is equal to sum over I sub I k omega k equals 1 to 3, and therefore the vector L is equal to the moment of inertia, or the inertial tensor times the vector of omega. So L is equal to I omega. Right, it had to come out like this, and it did. So now we've got a real collection of things. We have the kinetic energy and the angular momentum in the natural form there. This is a 3 by 3 matrix, and here you can see it was the matrix multiplication. Matrix times column vector, if you want to look at it that way. That was this I component, and then the dot product of those was the second sum. Okay, so we can gather all of those results together now. Okay, good. So now we can inspect and have a look at what this moment of this inertial tensor actually means. And what we'll see is it's a very familiar object, in fact. So we have rotational kinetic energy equals 1/2 Ij omega I omega j. That's our quadratic form. We have L equals I omega. And again, it's a matrix times a vector. And this I, which I'm showing as a matrix here, is this sum m r squared delta ij minus xi xj. One thing you're going to see immediately And you know, we'll even write this integral down again. dm over the body of the object r squared delta ij minus xi xj. Because we've been here before with these kind of things. We had 3xi xj last time. Now we just have xi times xj. Same thing's going to hold. A symmetric body, when you integrate over these, they're going to vanish. So when your body has enough symmetry and you have your origin at the center of mass, your off diagonals vanish. And that's what we're generally going to do. I, and that's a J. Okay, so I'm going to put that note right here already. If the body is symmetric, then off diagonals vanish. And a diagonal matrix isn't that bad to deal with. Okay. So the thing to do is actually write the whole thing out. Okay, we're going to write the whole thing out as a 3 by 3 matrix here. And just look at them. And we'll go ahead and use the summations. So the 1, 1, right, we have x1 squared plus x2 squared plus x3 squared minus x1 squared. So the 1, 1 here is sum of m x2 squared plus x3 squared. And the 1, 2, the ones that we know are typically going to vanish, m x, well, not ij, x1, x2. We could write the product or delta makes these vanish when we're off diagonal. M x1, x3 minus sine m x2, x1. You know, let's do the off diagonals first. M x2, x3 m x3, x1 minus m x3, x2. So what's going on the diagonal? We've already seen 1. Now for 2, 2, we have x1 squared plus x2 squared plus x3 squared minus x2 squared. So it's sum over m x1 squared plus x3 squared, and down here we're going to get sum over m x1 squared plus x2 squared. And these, you know, these are going to recognize. Go ahead and put a little red circle around each one. We're going to call these the principal moments in a while. And right, so for a symmetric body, these vanish. On the other hand, for an unsymmetric body, they're still here, and for a rotating unsymmetric body, they're going to give us the wobble. Okay, they're going to give us torques and stuff. But yeah, let's look at these principal moments of inertia on the diagonal. So this is the rotation about the x1 axis, or if you're rotating about the x1 axis, this is going to be your moment of inertia. And that's the distance from the x1 axis, x2 squared plus x3 squared. Likewise for the x2 squared axis, the distance from that axis of these masses is x1 squared plus x3 squared. Okay, so that's already looking good. And right, so there's actually nothing to be afraid of. These principal axes here are what we've already learned is the moment of inertia, but I'm sorry, these principal moments are just like the moments of inertia we've already learned about. Mass times distance from that axis. But now there are 3 possible axes. Okay. or 3 possible principal axes. Okay, now, a couple of ways we can go with this. Oh yeah, okay. So let's make sure we have all of this up here. That's good. So I can erase this. So my example now is rotation about a principal axis. Doesn't have to be a symmetric body yet. Okay. So the example, and I'll get a sketch to go with that. Rotation out a principal axis. So what we mean by that is that we have a body, and here's its body system, x1, x2, x3. We are requiring the origin to be at the center of mass, but as far as the mass distribution, we're not requiring it to be symmetric yet. So we have the full 3x3 tensor there. So rotation about a principal axis, and principal axis would be, so omega would be either omega, yeah, I could do this. Omega vector is equal to omega xi hat for one of these xi, x1, x2, x3, right, in the body frame. So it's the body frame, okay, and T, the kinetic energy, we can do first. Let omega equal omega x1 hat, right? There's its magnitude, there's the axis, the x1 axis. So that means omega equals omega 0, 0, right? And what do we get for the rotational kinetic energy? It's 1/2 sum over I sum over J, Ij, and omega I, omega J is just delta Ij. So omega squared delta Ij, we do it like that. Okay. Actually, let's go ahead and write it out though. Omega I, omega J. Okay. So what do we have? We have I11 omega 1 squared plus I12 omega 1 omega 2. So that's 0. Plus I13 omega 1 omega 3 0 plus I21 0 plus I22 omega 2 squared, and so forth. So this is how it should be, right? All of these vanish, and this is, since we were saying rotating about this one axis, this is the original kinetic energy definition. Okay. So all that complication goes away, and we're just left with 1/2 I11 omega squared. Okay. Now, the same simplicity doesn't obtain when we talk about the angular momentum, which I kind of like to do on this board here. But I don't have to. Yeah, maybe we should make some kind of note as to what just happened there. Okay. We're rotating about one principal axis. And by the way, we're treating it as a fixed principal axis. I'm not saying that this thing isn't going to wobble or want to wobble all over the place. Okay. We'll see with the angular momentum next that it's not that simple. But yeah, just say something about this, because that's just the familiar expression. So now we're going to do the angular momentum. And that's a matrix multiplication. And we're using the example that we have up above because, you know, arbitrary choice of axis. So for the angular momentum, I omega. Now remember, that's row times column. So the first row times that column there is I11 omega 1 plus I12 omega 2, I13 omega 3, but of course those vanish, okay? So I'm writing out a vector, of course. So I21 omega 1, that's fine. I22 omega 2, so we're going to end up with I21 omega 1, I31 omega 1. Okay, these are all zeros. For the vector L, vector L is equal to I21 omega 1. So it has three components. It has three components, and therefore L and omega are not parallel. Okay. So note, L and omega are not parallel. Okay. Not parallel. So that's the important takeaway right here. They're not parallel. When are they parallel? Well, remember, the omega vector just has that one component around the x1 axis. So if the body is symmetric and these two moments of inertia vanish, then it will be parallel. Yeah, let me consult here. That's all I have. They're not parallel. Okay, good. Very important result though, so I'll write that. They're not parallel. Note also, if the body is symmetric, then I21 equals 0, I22 equals 0, then L and omega are parallel. And L and omega are parallel. So I have a model, and it's actually not a physical model that I built, but I have a nice model situation that I'm going to draw on the board to explain all these things. That may be next time. No, we got a little more time. Okay, so they're not parallel, but as before, we're dealing with matrix times vector or with the quadratic form. And when we're talking about the rotation, we get back to a very basic and simple expression. If we're around a principal axis, when we talk about angular momentum, it's no longer as simple, but if the body is symmetric, then L and omega are parallel, which is again the intuitive basic situation. Okay. So actually, before we get to the dynamics, we'll do a bunch of definitions and maybe some integration theory as well. So yeah, I'll summarize what we have here, and then we'll go to calculations of the inertial tensor for different situations. And then we'll come back to this. So yeah, just to say, we could summarize these results so far. So we would say rotational kinetic energy, which of course was this quadratic form. And I'll do my picture again here. This is the body axis, so if we have rotation about a principal axis, I'm wondering if that's the right terminology. An axis of the body system. Calling it a principal axis may not be quite terminologically correct. Axis of the body system, okay. X1, X2, X3, then T, rotational kinetic energy. Point is, it's just M sub I, L sub I squared, as before. And that I showed clearly. And L equal I omega, not parallel, right? Because of the matrix multiplication, comma, but if the body is symmetric, then we have the parallel. Okay, symmetric, then L is parallel to omega. Okay, so we have that so far. That's the resume. This, from our standpoint, is just very basic. This is going to give rise to an interesting dynamics. The fact that L and omega are not parallel. So what we're going to do next is talk about some characterization of bodies and calculation of moments of inertia. And somewhere in my notes I have a little chapter on some integration theory that is interesting as well. good. Let's see. Actually, we're going to call it a day right here. So next time, we will do some properties of the inertial tensor. And so properties and then calculations of the inertial tensor before we get back to the dynamics. This point here, though, is looking ahead. This is the thing we have equations of motion for, so we'll translate them to equations of motion for the omega. Okay, but there's a few steps till we get there. Okay, good. See you guys next time.